Late November, 1944, Kure Naval Arsenal, Japan. The structural engineers stood in silence before a section of hull plating that should not have existed. Admiral Ozawa traced his fingers across the welded seam where American damage control teams had repaired a torpedo strike that should have sent this ship to the bottom. The captured Essex-class carrier section, salvaged from wreckage after the Battle of the Philippine Sea, contradicted everything Japanese naval architects had believed about carrier construction for the past decade. This fragment of USS Franklin, recovered after American forces abandoned damaged sections during emergency repairs at Ulithi Atoll, represented the first intact piece of an Essex-class carrier that Japanese engineers could examine without the chaos of combat obscuring the details. What they would discover in the months ahead would prove more devastating to Japanese naval confidence than any battle defeat. The sheer scale of American shipbuilding, when combined with the engineering sophistication evident in every welded joint and structural member, created a level of naval power projection that Japanese industry had never achieved and could never match. The transformation from enemy warship to intelligence windfall had begun 3 months earlier, on August 23, 1944. A Japanese submarine I-365, operating as part of the 4th Submarine Squadron, detected unusual salvage operations near Ulithi Atoll in the Western Caroline Islands. American repair crews were working frantically on a damaged carrier, cutting away sections of twisted hull plating damaged by a near miss from a Japanese bomber during operations in the Philippine Sea. The damaged sections, considered too heavy to transport back to Pearl Harbor for proper disposal, were being dumped in deep water offshore. Commander Tsukudo Hamazaki, commanding I-365, recognized an unprecedented intelligence opportunity. Rather than attacking the salvage vessels directly and alerting American forces to Japanese submarine presence in the area, he ordered his crew to mark the dump site coordinates and report them to Combined Fleet Headquarters. Within 48 hours, the submarine returned with specialized diving equipment and naval engineers trained in underwater salvage operations. The recovery operation took 6 days of dangerous work in waters that American patrol aircraft monitored regularly. Japanese divers worked at night, using minimal lighting to avoid detection, carefully cutting manageable sections from the larger pieces of wreckage that lay in relatively shallow water just beyond the atoll's protective reef. They selected pieces that showed construction techniques, structural design, and material specifications. Hull plating with its distinctive welding patterns, bulkhead sections showing compartmentalization design, elevator machinery fragments revealing American approaches to aircraft handling systems. By September 2nd, I-365 departed Ulithi with approximately 8 tons of carrier wreckage secured in cargo nets and lashed to her deck. The submarine traveled submerged during daylight hours, surfacing only at night to recharge batteries and ventilate the cramped interior. The journey to Kure Naval Arsenal took 11 days, with the submarine making wide detours to avoid American patrol routes and known submarine hunting grounds. When I-365 finally slipped into Kure's protected harbour on September 13, 1944, she carried intelligence that would fundamentally alter Japanese understanding of their enemy's capabilities. Within hours of the submarine's arrival, engineers from the Navy Technical Department swarmed over the recovered wreckage. They photographed every piece from multiple angles before moving it to secure facilities inland, away from potential American bombing raids that were beginning to reach even Japan's home islands with increasing frequency. The initial examination, conducted over 3 days of intensive work, revealed construction techniques that contradicted Japanese assumptions about American shipbuilding methods. The hull plating showed uniform thickness maintained across large panels, indicating precision rolling mills and quality control that Japanese industry struggled to match under wartime conditions. The welding seams demonstrated consistency, suggesting automated or semi-automated welding processes rather than individual craftsmen working by hand, allowing faster construction with fewer skilled workers. The steel alloy composition, determined through metallurgical analysis at naval laboratories, showed sophisticated metallurgy combining strength with weldability, something Japanese shipyards found increasingly difficult to achieve as high-grade alloying elements became scarce. The structural spacing and member dimensions revealed design margins substantially exceeding minimum requirements, suggesting American engineers built excess strength into their carriers for future modifications and battle damage resilience. Every detail pointed to the same, uncomfortable conclusion. American shipbuilding operated at a scale and sophistication level that Japanese industry, despite its pre-war advantages in certain specialized areas, had never achieved and could not match during wartime conditions. The wreckage fragments moved to the Navy Technical Research Institute at Kamakura, approximately 30 miles south of Tokyo, where Japan's most experienced naval architects worked on warship design and evaluation. Here, the recovered materials would undergo months of exhaustive examination that would reveal the full extent of American advantages in carrier construction. November 1944 brought the first comprehensive technical reports from Kamakura that circulated through Combined Fleet Headquarters and the Navy Ministry. The documents, classified as most secret and distributed only to senior officers and technical specialists, painted a sobering picture of comparative capabilities that shattered comfortable assumptions about American naval architecture. The Essex-class carriers represented a fundamental rethinking of carrier design philosophy that Japanese planners had not anticipated. Where Japanese carriers emphasized speed and aircraft capacity over protection and damage control, American designers built ships that balanced all requirements with particular attention to survivability under battle conditions. This philosophy showed in every structural detail the recovered wreckage revealed. The hull construction used what American naval architects called unit assembly, where large prefabricated sections built in different areas of the shipyard came together during final assembly. This modular construction dramatically reduced building time compared to traditional methods where the entire ship was assembled sequentially from keel to superstructure. Japanese shipyards still used largely traditional construction methods, requiring sequential assembly and extensive on-site fitting, limiting the number of workers who could work simultaneously and extending construction schedules. But the statistics that troubled most Japanese naval architects concerned construction time and industrial capacity. The first Essex-class carrier, USS Essex herself, laid down on April 28, 1941, launched on July 31, 1942, and commissioned on December 31, 1942. Total construction time from keel laying to commissioning, 20 months. Subsequent carriers in the class achieved progressively shorter construction times as American shipyards refined production methods and trained workers. USS Intrepid, fourth ship of the class, completed in 16 months. USS Hornet, eighth ship, finished in 14.5 months. Essex-class carriers at intervals of approximately 6 weeks, a production rate that seemed physically impossible to Japanese observers accustomed to construction schedules measured in years. Japanese intelligence analysts determined that American shipyards had laid down at least 24 Essex-class carriers by mid-1944. By comparison, Japan's entire carrier construction program from 1920 through 1944 had produced only 25 fleet carriers of all types, and many of those had been sunk by this point in the war. The implications were strategically devastating for any objective observer who understood industrial production. Even if Japanese naval aviation achieved favorable loss ratios in carrier battles, even if Japanese pilots and tactics proved superior in individual engagements, American industry could replace losses faster than combat could inflict them. The detailed technical examination at Kamakura proceeded systematically through the winter of 1944 into early 1945. Teams of specialists studied specific systems and construction features, documenting their findings in technical reports that would influence Japanese understanding of American capabilities, even as the strategic situation deteriorated rapidly. The compartmentalization design revealed American obsession with damage control and ship survivability that went far beyond Japanese practice. The recovered bulkhead sections showed extensive subdividing of the hull into hundreds of watertight compartments, each capable of isolation through quick-acting doors and valves if flooding occurred. Japanese carriers, designed when fuel efficiency and speed took precedence over protection, featured fewer, larger compartments that made them vulnerable to progressive flooding. A single torpedo hit could flood multiple compartments before damage control teams could contain the breach. The Americans, learning from British experience and their own early war losses, built ships where damage remained localized through aggressive compartmentalization that limited flooding spread. The examination team calculated that an Essex-class carrier could survive approximately 3 torpedo hits to the hull below the waterline before losing buoyancy reserves needed to remain afloat, assuming reasonably effective damage control by trained crews. Japanese fleet carriers of the Shokaku class, Japan's best pre-war designs, would likely sink from 2 torpedo hits in comparable locations and might succumb to a single hit if it struck near machinery spaces or magazines. The machinery spaces examination revealed American approaches to power plant design that impressed Japanese engineers despite their own considerable expertise in marine engineering. The 8-boiler, 4-turbine arrangement provided substantial redundancy that kept the carrier operational even with significant machinery damage. Japanese carriers typically used fewer, larger boilers concentrated in fewer, larger machinery spaces, a more efficient arrangement from a thermodynamic perspective that reduced weight and improved fuel economy. But this efficiency came at the cost of vulnerability. The armor protection scheme demonstrated another area where American and Japanese design philosophy diverged. The Essex-class carriers incorporated substantial armor in critical areas, particularly around the machinery spaces, magazines, and aviation fuel storage. The flight deck used special treatment steel 3 inches thick in areas over vital spaces, sufficient to detonate bombs before they penetrated to the hangar deck below. Japanese carriers featured minimal armor, relying instead on speed, maneuverability, and defensive fighters to avoid hits rather than surviving them. This philosophy made sense when carriers were expected to strike first with powerful air groups that would destroy enemy carriers before they could attack, winning battles through offensive capability rather than defensive resilience. The examination of aviation fuel systems revealed perhaps the most sophisticated engineering in the entire carrier design. The Essex class incorporated self-sealing fuel tanks for aviation gasoline storage, a technology the Japanese understood theoretically but never implemented successfully at large scale. The self-sealing tanks used multiple layers of rubber and fabric that swelled when exposed to fuel, automatically closing bullet or shrapnel holes before significant fuel loss occurred. This technology, combined with extensive fire suppression systems throughout the fuel distribution network, gave American carriers substantial resistance to the catastrophic fires that had destroyed several Japanese carriers when single bomb hits ignited aviation fuel vapors. Japanese carriers stored aviation fuel in simple steel tanks without self-sealing capability, making them vulnerable to fires that could rage through fuel distribution systems once ignited. The examination team interviewed survivors from Japanese carrier losses, gathering first-hand accounts of damage control attempts and system failures during battle. Survivors from the Shokaku, sunk at the Battle of the Philippine Sea on June 19, 1944, described how a single torpedo hit from the submarine USS Kavala had triggered gasoline vapor explosions that progressively destroyed the ship over 3 hours. Damage control teams fought valiantly, but lacked the equipment, training, and ship systems needed to contain the damage. Survivors from the Taiho, Japan's newest carrier also sunk on June 19, described similar cascading failures following a single torpedo hit that initially seemed survivable. An inexperienced damage control officer ordered continued ventilation, thinking fresh air would dilute the vapors, but instead spread them throughout the ship. Hours later, a single spark triggered massive explosions that blew out the sides of the ship and ignited uncontrollable fires. The examination team compared these disaster sequences with American carrier damage experiences. USS Franklin survived devastating bomb hits off Japan in March 1945 that triggered fires and explosions, killing more than 700 crew members. The carrier remained afloat through extraordinary damage control efforts and was eventually repaired and returned to service, demonstrating the survivability that American damage control engineering provided. By late January 1945, the technical examination had revealed enough about Essex-class capabilities that Navy Ministry planners could no longer maintain comforting illusions about competitive parity with American carrier forces. The captured wreckage had provided a window into American shipbuilding that confirmed what intelligence analysts had suspected but couldn't prove definitively. America possessed industrial capacity and engineering sophistication that Japan could not match through any realistic means. The strategic implications demanded reassessment of Japanese naval strategy. But by this point in the war, strategic alternatives had narrowed to the point where meaningful choices no longer existed. The combined fleet had been shattered at the Battle of Leyte Gulf in October 1944, losing 4 carriers along with battleships, cruisers, and destroyers in a desperate gamble to disrupt American operations in the Philippines. Even if Japanese industry could somehow match American carrier construction, which the examination proved impossible, Japan lacked the fuel to operate them, the pilots to fly from them, and the escorts to protect them. The examination of Essex-class wreckage simply confirmed what every informed Japanese officer already understood but might not openly acknowledge. The detailed technical reports from Kamakura circulated through what remained of Japan's naval command structure in February 1945. Senior officers gathered at Navy Ministry headquarters in Tokyo to review findings that quantified their worst fears about American capabilities. Admiral Soemu Toyoda, Commander-in-Chief of the Combined Fleet, studied the technical summaries with professional detachment that masked private despair. The numbers told an unambiguous story about relative industrial capacity and shipbuilding sophistication. America had commissioned 9 Essex-class carriers in 1943 alone, more than Japan's entire fleet carrier construction from 1937 through 1942. The examination team had prepared detailed comparisons between the Essex-class design and Japan's various carrier classes, highlighting specific areas where American engineering exceeded Japanese capabilities. Construction time comparisons showed the starkest disparity. Essex-class carriers reached operational status in 14 to 20 months from keel laying to commissioning. Japanese fleet carriers required 36 to 48 months under optimal conditions, and wartime conditions were far from optimal. American shipyards achieved rapid construction through comprehensive standardization that Japanese shipbuilding never matched. Every Essex-class carrier used identical hull dimensions, machinery arrangements, and major equipment installations that allowed workers to develop expertise through repetition. Japanese carriers, designed individually with unique features reflecting different construction periods and evolving operational requirements, required custom fabrication of most components. The examination team calculated that American shipyards could build Essex-class carriers using approximately 60% of the man-hours Japanese yards required for comparable tonnage. This productivity advantage came from multiple sources, including better tools and equipment, more efficient work organization, superior welding techniques, and most importantly, the standardization that allowed workers to repeat identical tasks until they achieved exceptional speed and quality. Japanese shipyard productivity had actually declined through the war years as experienced workers left for military service or were killed in American bombing raids. Replacement workers, often women and older men without previous shipbuilding experience, struggled to match pre-war quality standards despite heroic efforts. The damage control system examination revealed the most significant disparity between American and Japanese carrier design. Essex-class carriers incorporated sophisticated damage control systems designed by engineers who studied British and early American combat experience. Compartmentalization divided the hull into more than 2,000 watertight compartments, each capable of isolation if flooding occurred. The fire suppression system incorporated automated foam dispensers throughout the hangar deck and fuel distribution network, allowing rapid response to fires before they spread out of control. Ventilation systems included dampers and isolation valves that prevented smoke and toxic gases from spreading through the ship. The electrical system used multiple generators distributed throughout the ship with cross-connections, allowing any generator to power any system through redundant cabling runs. This prevented single hits from causing total electrical failure that would disable pumps, lighting, and communications. The examination team compared these systems with American carrier damage experiences documented through intelligence reports. American carriers had absorbed comparable or worse damage and survived through effective damage control enabled by superior ship systems. The comparison suggested that American carriers could absorb approximately 3 to 4 times the damage Japanese carriers could survive before sinking. The aircraft handling system examination revealed American innovations that improved operational efficiency. The Essex-class design incorporated 3 elevators connecting the hangar deck to the flight deck, each capable of lifting fully armed and fueled aircraft in less than 30 seconds. The deck-edge elevator design used on 2 of the 3 elevators moved aircraft outside the ship's hull structure, preventing elevator damage from affecting flight operations. The examination team calculated that an Essex-class carrier could launch a full strike group of 36 aircraft in approximately 30 minutes under optimal conditions. Japanese fleet carriers required 45 to 60 minutes for comparable operations. This difference accumulated across multiple launches during daylight operations, allowing American carriers to generate approximately 25% more sorties during typical combat days. By March 1945, the Kamakura examination had accumulated enough data to produce comprehensive reports comparing American and Japanese carrier capabilities across all major categories. The reports provided quantified assessments of relative capabilities that confirmed what combat experience had already demonstrated. American carriers outperformed Japanese carriers in nearly every measurable category that mattered for sustained combat operations. The reports quantified production disparities that strategic planners had understood conceptually but never confronted with such stark evidence. Between December 1941 and August 1945, American shipyards commissioned approximately 100 aircraft carriers of all types. Japanese shipyards commissioned 17 carriers of all types during the same period. The 17 to 100 disparity in production told the entire story of the carrier war in the Pacific. No amount of tactical sophistication or individual courage could overcome such overwhelming material advantage sustained over years of conflict. The examination team calculated that American shipyards were building carriers faster than combat could sink them even during peak combat intensity in 1944. Japanese carrier losses, by contrast, could never be adequately replaced given industrial limitations and resource shortages. The strategic assessments prepared by Navy Ministry planners in April 1945 incorporated the technical findings from Kamakura into broader analyses of Japan's naval position. The assessments acknowledged that Japan had fundamentally misunderstood American industrial capacity and the implications for sustained naval warfare. Pre-war Japanese naval planning had assumed that American industrial advantages would be offset by geography, logistics challenges, and Japanese tactical superiority developed through intensive training. Every assumption had proven catastrophically wrong. American carriers were not inferior but superior in critical areas including damage control, aircraft handling efficiency, and operational sustainability. Most fundamentally, Japan had miscalculated American national will and industrial determination. Japanese planners assumed that early defeats and mounting casualties would erode American public support for continuing the war. The assumption reflected profound misunderstanding of American political culture. Rather than eroding support, early defeats like Pearl Harbor galvanized American determination and unleashed industrial mobilization that exceeded even optimistic American predictions. The Kamakura examination provided physical evidence of this industrial mobilization in ways that intelligence reports had suggested but never proven definitively. The recovered Essex-class wreckage was tangible proof that American industry could build sophisticated warships, incorporating advanced technology at rates multiple times faster than Japanese industry. The comparison grew more painful when analysts examined specific categories. American shipyards commissioned 19 escort carriers in 1944. Japanese industry attempted escort carrier construction, but completed only 4 vessels through the entire war, and those 4 achieved minimal operational service before being sunk or immobilized by fuel shortages. By May 1945, the strategic situation had deteriorated beyond any possibility of reversal through military operations. American forces occupied Okinawa, providing bases within fighter range of Japan's home islands. American carriers operated freely in Japanese coastal waters. Japan's remaining naval forces had been reduced to insignificance through years of attrition and fuel shortages. The examination of American carrier wreckage had revealed why this catastrophic decline had occurred, despite Japanese tactical skill and individual courage. American industry had simply overwhelmed Japanese capacity through production rates that Japan could never match or counter through any realistic means. The technical reports from Kamakura circulated through what remained of Japanese Naval Command, providing detailed documentation of American advantages across every category that mattered for carrier operations. But by this point, the reports served primarily as historical documentation rather than operational intelligence. Admiral Ozawa, who had commanded carrier forces at the Battle of the Philippine Sea, reviewed the Kamakura reports with professional interest, tempered by recognition that the information had become historically valuable rather than operationally relevant. The reports quantified what he had understood intuitively through combat experience. The reports included one section that particularly captured Ozawa's attention, comparing pilot training programs between American and Japanese naval aviation. Pre-war Japanese naval aviation had emphasized intensive training that produced exceptionally skilled pilots after years of instruction. The program worked brilliantly when producing relatively small numbers of pilots for peacetime fleet operations, but proved inadequate for wartime attrition. American naval aviation training emphasized volume production of adequately trained pilots through streamlined programs. Individual American pilots might be less skilled than Japanese counterparts early in their service, but adequate training combined with superior equipment and numerical advantage compensated for individual skill differences. More importantly, American training programs produced replacement pilots faster than combat killed them. The examination team had interviewed surviving Japanese carrier pilots who had faced American carrier aircraft in combat. The interviews revealed grudging respect for American equipment, combined with frustration at tactical disadvantages created by numerical inferiority. Japanese pilots consistently praised American aircraft performance, particularly the Grumman F-6F Hellcat fighter. American fighters incorporated substantial armor protection around cockpits and fuel tanks, accepting weight penalties that reduced maneuverability but dramatically improved pilot survival when hit. Japanese fighters, designed when fuel efficiency and performance took precedence over protection, featured minimal armor and unprotected fuel tanks that made them vulnerable to fires. The pilot survival rate comparison revealed stark differences. American carrier pilots shot down over water had reasonable chances of rescue through comprehensive search and rescue operations. Japanese pilots shot down in similar circumstances faced minimal rescue prospects, leading to high casualty rates even among pilots who survived being shot down. The examination team's final report, completed in June 1945, summarized findings in language that avoided explicit defeatism but conveyed unmistakable conclusions about Japan's naval position. American carrier construction, aircraft production, and pilot training had created naval aviation superiority that Japan could not counter through any available means. The report noted that understanding enemy capabilities didn't eliminate them or suggest counters when resources didn't exist. Japanese naval officers who examined American carrier wreckage learned valuable technical lessons about ship design, damage control, and systems integration. But knowledge proved operationally useless without industrial capacity to implement improvements or strategic circumstances permitting new construction. The examination of American carrier wreckage had provided Japanese naval architects with detailed understanding of why American carriers outperformed Japanese carriers across nearly every category that mattered for sustained operations. But the most important revelation concerned industrial capacity rather than technical capability. Japanese industry, struggling with resource shortages, workforce depletion, bombing damage, and submarine blockade, could never approach such production levels, regardless of technical knowledge or engineering skill. The examination team calculated that Japan would require approximately 15 years to match American naval construction from 1941 through 1945, assuming peacetime conditions with unlimited resources and no combat losses requiring replacement. The war ended in August 1945, following atomic bomb attacks on Hiroshima and Nagasaki and Soviet entry into the Pacific War. Japan's surrender terminated the examination program at Kamakura before final reports could be completed and distributed. American occupation forces seized the facility and its documentation, preserving technical reports that provided detailed evidence of how Japanese engineers understood American capabilities. The examination of Essex-class wreckage had revealed fundamental differences in tangible form that Japanese engineers could measure, analyze, and document with scientific rigor. Most significantly, the examination proved that American advantages stemmed not from superior theoretical knowledge, but from comprehensive industrial infrastructure developed through decades of commercial shipbuilding and civilian manufacturing. American shipyards applied mass production techniques perfected in automobile manufacturing to warship construction, achieving productivity levels that traditional shipbuilding methods could never match. Japanese shipyards, lacking comparable civilian industrial base and mass production experience, continued using traditional methods requiring skilled craftsmen and custom fabrication. The story of Japanese examination of American carrier wreckage represents a peculiar footnote to the larger Pacific War narrative. Engineers working in secure facilities analyzed enemy equipment with scientific thoroughness, producing detailed reports quantifying American advantages. But the examination occurred too late in the war to influence operations or suggest realistic countermeasures. The engineers at Kamakura had answered the question of why American carriers proved superior through systematic analysis of captured wreckage. But the examination couldn't answer the more fundamental strategic question of how Japan could have matched American industrial production given realistic resource constraints and geographic disadvantages. The mathematics of industrial attrition had determined strategic outcomes long before Japanese engineers completed their technical examination. Understanding the enemy's material advantages didn't eliminate them or suggest counters when the industrial base needed to implement changes had been systematically destroyed. Admiral Ozawa survived the war and participated in post-war analysis of Japanese naval operations. He acknowledged that Japan had fundamentally miscalculated American industrial capacity and the implications for sustained carrier warfare. Pre-war intelligence had identified American shipbuilding potential but underestimated mobilization speed and production rates once war began. The examination of Essex-class wreckage had provided tangible evidence of these American advantages in ways that intelligence reports never achieved. Japanese engineers could measure welding quality, test material strength, analyze structural arrangements, and document systems integration with scientific precision. The carrier fragment that arrived in Japan aboard submarine I-365 in September 1944 had traveled thousands of miles from its origin as part of USS Franklin's hull to become intelligence material in Japanese laboratories. The journey symbolized the larger Pacific War story, where American industrial production created such abundance that even scrap metal contained lessons about enemy capabilities. But ultimately, the fragment was simply evidence of material disparity that determined strategic outcomes through arithmetic too fundamental for tactics or courage to overcome. American shipyards built Essex-class carriers faster than Japanese forces could sink them. This simple fact explained Japanese defeat in the carrier war more completely than any amount of tactical analysis. The wreckage remained at Kamakura until American occupation forces seized the facility in September 1945. The fragment was eventually shipped to the United States along with Japanese technical reports, where it became part of naval intelligence archives. That fragment had taught Japanese engineers everything worth knowing about why American carriers outperformed Japanese carriers in sustained combat operations. The examination of American carrier wreckage represents the final chapter in Japan's failed carrier warfare campaign, providing historical documentation of how Japanese engineers understood their defeat even as they experienced it. The technical reports from Kamakura offer insights into Japanese technical sophistication and professional acknowledgement of American advantages. But the reports also document the futility of understanding enemy capabilities without possessing industrial means to counter them. The Essex-class carriers kept coming, every 6 weeks during peak production, each one incorporating lessons from previous ships and combat experience. American industry delivered them faster than combat could sink them, maintaining and expanding carrier strength throughout the Pacific War. Japanese engineers who examined recovered wreckage understood exactly why this occurred and documented their findings with scientific precision. But understanding provided no comfort and suggested no realistic countermeasures when industrial capacity to implement changes had been destroyed by the very forces whose capabilities the examination revealed. The technical reports from Kamakura reached their final audience in July 1945, distributed to what remained of Japan's naval leadership in heavily redacted form. The original documents, running to more than 800 pages of detailed technical analysis, had been condensed to executive summaries that senior officers could digest during the crisis atmosphere of Japan's final weeks. Commander Yoshio Nakamura, who had supervised much of the metallurgical analysis, spent the last weeks before surrender attempting to preserve documentation that might otherwise be destroyed. He understood that the examination had produced knowledge valuable beyond immediate military applications. The reports documented Japanese technical capabilities and analytical methods as much as American advantages, providing evidence that Japanese engineers had understood their situation with remarkable clarity. Nakamura organized the technical documentation into 3 categories: the most sensitive materials, detailing specific American construction techniques and material specifications, were hidden in sealed containers that might survive American occupation. Less sensitive technical drawings and photographs were consolidated for potential destruction if ordered. The analytical summaries and comparative assessments were prepared for probable seizure by occupation forces, organized to demonstrate Japanese cooperation and technical sophistication. American naval intelligence officers who seized the Kamakura facility in September 1945 discovered documentation far exceeding their expectations. Lieutenant Commander Robert Whitmore, assigned to evaluate captured Japanese naval documents, spent 3 weeks reviewing the examination reports with growing professional respect for Japanese analytical thoroughness. The reports demonstrated that Japanese engineers had correctly identified nearly every significant advantage built into Essex-class design. The comparative assessments showed sophisticated understanding of shipbuilding productivity, damage control engineering, and systems integration. Whitmore's preliminary evaluation concluded that Japanese technical understanding had been excellent, their analysis rigorous, and their conclusions accurate regarding American industrial advantages. What surprised Whitmore most was the examination team's willingness to document uncomfortable truths about Japanese disadvantages without apparent attempt to soften findings for political palatability. The reports acknowledged Japanese inferiority across most categories with scientific detachment that suggested engineers valued accuracy over nationalist pride. The American evaluation team interviewed surviving Japanese engineers who had worked on the examination. These interviews revealed that the examination had proceeded with full awareness that findings would not influence war outcomes. Several engineers stated explicitly that they had viewed their work as documentation for historical record rather than operational intelligence. Commander Nakamura, when interviewed, explained the examination's real purpose as he understood it. "We knew the war was lost by the time we began detailed analysis. But we wanted to understand exactly why we lost, not for propaganda purposes or to excuse failures, but because engineers must understand their mistakes completely or they learn nothing valuable." This attitude impressed American interviewers, who noted in their reports that Japanese technical personnel displayed remarkable professional objectivity about defeat. The examination documents became valuable to American analysts, not primarily for revealing Japanese understanding of American capabilities, but for demonstrating Japanese self-awareness about their own limitations. The final American compilation of carrier production statistics, completed in late 1945, quantified the industrial disparity that the Kamakura examination had attempted to analyze. American shipyards commissioned 99 aircraft carriers between December 1941 and August 1945. The breakdown revealed production rates that accelerated throughout the war, despite increasing complexity of carrier designs. Fleet carriers, 24 Essex-class ships commissioned, with an additional 8 under construction when the war ended. Light carriers, 9 Independence-class conversions from cruiser hulls. Escort carriers, 66 vessels produced primarily by Kaiser shipyards using assembly line techniques adapted from merchant ship construction. Japanese carrier production during the same period, 17 ships of all types commissioned, including conversions from other vessel types and several ships that achieved only token operational service before fuel shortages immobilized them. The production disparity extended beyond simple numbers to encompass aircraft production, pilot training, and logistical support. American industry produced approximately 99,000 carrier-capable aircraft during the war. Japanese industry produced approximately 33,000 carrier-capable aircraft, and production quality declined significantly in final war years as material shortages and workforce depletion took effect. American naval aviation training programs graduated approximately 60,000 carrier-qualified pilots during the war. Japanese programs graduated approximately 11,000 carrier pilots, and attrition exceeded replacement rates after mid-1943, creating pilot shortages that rendered surviving carriers less effective, even when fuel permitted operations. The post-war analysis of the Kamakura examination revealed insights valuable to both American and Japanese naval architects. American designers learned that their damage control emphasis had been correctly prioritized, as Japanese engineers had identified survivability as the most significant advantage in Essex-class design. The examination documents also revealed areas where Japanese engineers had developed superior solutions to specific problems. Japanese optical rangefinders exceeded American equivalents in precision and range. Japanese torpedo technology, particularly the oxygen-fueled Type 93 torpedo, represented genuine innovation that American forces had struggled to counter during early war operations. But these isolated advantages could not compensate for systemic disadvantages in industrial capacity, logistics, and strategic resources. The examination had documented this asymmetry with precision, showing that tactical advantages in specific systems proved irrelevant when strategic production disparities reached orders of magnitude difference. American naval architects incorporated lessons from the examination into post-war carrier designs. The Midway-class carriers, designed during the war but commissioned afterward, reflected American understanding that future carrier design should emphasize damage control and operational sustainability even more than Essex-class ships had achieved. The examination team at Kamakura had approximately 120 engineers, technicians, and support personnel working over 9 months to analyze the recovered wreckage. Many of these individuals lost family members to American bombing raids during the examination period, yet continued their technical work with professional discipline. Several team members kept private journals documenting their emotional response to analyzing enemy equipment while their nation suffered catastrophic defeat. These journals, recovered decades later, revealed complex feelings about their work. Pride in technical competence, mixed with awareness that their analysis documented Japanese inadequacies. Respect for American engineering combined with grief over Japanese losses. One engineer, Takeshi Yamamoto, wrote in March 1945, "Today we calculated that American shipyards completed another Essex-class carrier while we worked on this analysis. The carrier we study in fragments, they build complete in the time we take to understand a single section. This is the mathematics of our defeat, written in steel and welding flux." Another entry from April. "The American welding is beautiful, perfect penetration, consistent bead spacing, minimal distortion. This is not military technology but industrial art. We could do this on a small scale with master craftsmen. They do this at scale with ordinary workers and automated equipment. The difference explains everything." The Essex-class wreckage fragment and associated documentation began a long archival journey through American naval intelligence systems. Initially classified as restricted material, the documents were studied by naval architects designing post-war carriers. The physical wreckage fragment underwent additional metallurgical analysis at American laboratories, confirming Japanese findings about steel composition and fabrication methods. By the 1950s, the examination documents had been partially declassified and incorporated into American naval architecture curricula as examples of foreign technical intelligence analysis. Students studied the reports as demonstrations of thorough technical evaluation conducted under adverse conditions. The physical wreckage fragment eventually reached the Smithsonian Institution, where it became part of naval history collections. Museum curators recognized the fragment's historical significance not as battle damage, but as evidence of intelligence operations and technical analysis during wartime. Military historians analyzing the Pacific War in subsequent decades used the Kamakura examination documents as primary sources for understanding Japanese awareness of American capabilities. The documents demonstrated that Japanese defeat resulted not from ignorance of American advantages, but from inability to counter them, despite clear understanding. This distinction proved important for post-war strategic analysis. Some American analysts had assumed Japanese military leaders suffered from wishful thinking about enemy capabilities. The Kamakura documents showed instead that at least some Japanese officers understood their situation with painful clarity, but lacked realistic options for changing strategic trajectories determined by industrial capacity differences. Admiral Chester Nimitz, reviewing the examination documents in 1946, wrote a marginal note that captured this recognition. They knew, they understood what we could do and what they couldn't match. But knowing changed nothing when industrial facts were unalterable. The examination technique developed at Kamakura influenced post-war intelligence methodology for analyzing foreign military equipment. The systematic approach, proceeding from visual inspection through metallurgical analysis to systems integration evaluation, became standard procedure for technical intelligence collection. American intelligence agencies adopted similar methodologies when examining Soviet military equipment during the Cold War. The comprehensive documentation, comparative analysis, and quantified assessments pioneered at Kamakura set standards for technical intelligence, reporting that persisted for decades. Japanese engineers who survived the war and worked in reconstruction efforts sometimes encountered American naval architects during technical conferences in the 1950s. These meetings occasionally produced uncomfortable moments when former enemies discussed the examination that had quantified Japanese defeat with scientific precision. Commander Nakamura, who became a professor of naval architecture at Tokyo University after the war, maintained correspondence with American colleagues who had interviewed him during the occupation. One letter from 1958 reflected on the examination's meaning. "We measured your advantages with calipers and micrometers, reducing national catastrophe to technical specifications. Perhaps this was necessary for engineers to process defeat, convert strategic disaster to metallurgical analysis, and grief becomes merely data to be documented." The examination of Essex-class wreckage at Kamakura represented a unique confluence of technical curiosity, intelligence opportunity, and historical documentation. Japanese engineers had conducted rigorous analysis of enemy equipment while their nation collapsed around them, producing reports that acknowledged defeat through scientific objectivity. The examination could not change strategic outcomes determined by industrial capacity differences too fundamental for tactics or courage to overcome, but the documentation preserved evidence of Japanese technical sophistication and professional integrity during the catastrophic national crisis. The wreckage that traveled from Ulithi Atoll to Kure Naval Arsenal to Kamakura Research Facility to American archives had accumulated meanings beyond its physical characteristics. It represented the Japanese understanding of American industrial power. It documented the moment when technical analysis confirmed strategic fears. It provided evidence that knowledge of enemy capabilities offered no comfort when industrial means to respond had been destroyed. The Essex-class carriers continued their service long after the examination ended. Several ships served through the Vietnam War, modernized and updated but still recognizable as the design Japanese engineers had studied with such thorough attention. The examination had captured a moment in carrier evolution, preserving technical analysis of ships that would serve for decades beyond the conflict that prompted the investigation. The final irony was that Japanese engineers who examined American carrier wreckage in 1944 had analyzed technology their nation would eventually master in different form. Japan's post-war maritime industry became globally dominant in commercial shipbuilding, applying industrial techniques and quality control methods that paralleled American wartime innovations. But that transformation occurred decades after the examination concluded, emerging from reconstruction rather than wartime necessity. The engineers at Kamakura had documented defeat with precision, not anticipating that their nation would eventually apply similar industrial sophistication to peaceful purposes, building commercial vessels that dominated world markets through the very productivity advantages they had studied in enemy warships. The examination of American carrier wreckage ended not with conclusions that might alter strategy, but with documentation that explained why strategy had failed. The reports from Kamakura stand as testament to engineering professionalism maintained during national catastrophe, technical analysis conducted when outcomes were already determined, and scientific documentation preserved for historical understanding rather than operational advantage. The Essex-class fragment, that section of hull plating cut from USS Franklin and analyzed with such thoroughness at Kamakura, remains in archival storage as physical evidence of these events. The welding seams that Japanese engineers found so impressive still show the quality control and industrial sophistication that characterized American wartime shipbuilding. The fragment represents not just naval architecture but industrial capacity, not just technical design but national will, not just enemy capability but historical inevitability written in steel. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.